On October 3rd, as 3i Atlas made its closest pass to Mars, the data stream went quiet. For nearly 36 hours, NASA's tracking dashboards froze. No telemetry, no orbital updates, no camera feed. The official reason, a partial US government shutdown, sounds procedural, but the timing isn't. Because those missing hours coincide precisely with the moment Atlas crossed the Martian orbital path, a region where two active probes, ESA's ExoMars and NASA's MAVEN, should have had clear visibility. When the feed resumed, the coordinates didn't quite match predictions. Atlas was slightly off course, not by much, but enough to raise questions. Its morphology remained compact, its signature strangely dim, and most importantly, there was no visible tail. Astronomers from Prague to Pasadena noted the same thing. The object looked solid. No debris cloud, no classic coma structure. Yet something was emanating from its surface, a faint directional jet aimed toward the sun. Whatever happened during that blackout window, the numbers stopped adding up. And tonight, we're going to unpack why. Because what's happening to 3i Atlas right now is something no comet has ever done, and it's forcing scientists to quietly reconsider what this object really is. When Atlas approached Mars, everything should have been routine. NASA's Parker Solar Probe had a distant view, MAVEN was in orbit, and the European Space Agency's ExoMars Trace Gas Orbiter was positioned for continuous observation. The timing couldn't have been better, or worse. Because just as the object entered the Martian observational corridor, the United States government partially shut down. Within hours, public-facing data feeds began dropping offline. Mission dashboards that had run without interruption for months suddenly went dark. The Minor Planet Center's tracking logs froze at timestamp 2025-10-3T-2100 UTC. Even the Deep Space Network, which usually keeps redundant telemetry archives, lagged in posting its relay timestamps. To most, it looked procedural, a bureaucratic pause. But for researchers tracking Atlas's orbit in real time, that blackout was catastrophic. The flyby geometry, a near-perfect line between Mars, the Sun, and the inbound interstellar object, offered the best opportunity to measure its mass through subtle gravitational perturbations. Losing those data meant losing the cleanest comparison window in the entire observation campaign. When feeds resumed, Atlas's coordinates were subtly off, about 0.04 astronomical units from the expected vector. Statistically small, but enough to alter its projected perihelion timing by several hours. The discrepancy suggested either a transient force acting on the object or an incomplete dataset patched post-event. ESA's ExoMars team released limited imagery days later. Their frames showed a dim, compact nucleus with no defined tail, just a short haze trailing sunward. It didn't behave like a comet. It behaved like something preserving its shape under solar stress. Some astronomers proposed mundane explanations: miscalibrated photometry, image stacking artifacts, solar wind turbulence. Others noticed that this wasn't the first time a near-Mars encounter had coincided with an unexplained data stall. It had happened faintly during Borisov's 2019 trajectory as well, though not this completely. That's what makes this blackout different. It didn't just obscure the view, it coincided precisely with the point where Atlas should have shown maximum physical activity, the moment when volatile compounds normally erupt into visible outgassing. Instead, silence. And when visibility returned, nothing fit. No tail, no debris signature, no measurable dust plume, just a stable, compact body gliding along the ecliptic as if it hadn't interacted with the sun at all. So the question emerged: did Atlas change during the blackout, or did the instruments simply stop reporting what they saw? Because if the latter is true, someone chose to keep those readings quiet. From the start, Atlas looked wrong. Every major comet on record, from Hale-Bopp to C 2023A3, displays a predictable morphology. A bright nucleus surrounded by a diffuse coma, streaming gas and dust away from the sun. But 3i Atlas defies that pattern entirely. Its brightness profile remains sharply peaked, the light curve almost flat, like that of a rocky asteroid rather than as icy wanderer. Early Hubble imagery should have clarified the issue. Instead, it deepened it. The telescope's fine guidance sensors detected no extended coma. The surface reflectivity stayed constant across multiple exposures, unusual for a body supposedly venting volatile gases. When the same region was imaged again 2 weeks later, the object's luminosity barely shifted, even though solar flux had nearly doubled as it closed the gap toward the Sun. That constancy shouldn't happen. Cometary bodies brighten exponentially with solar proximity. Atlas didn't. Its apparent magnitude curve sat stubbornly still, a straight line where physics demanded a steep rise. Researchers tried to fit the data to existing models. Maybe the coma was too compact to resolve, or the tail aligned perfectly with the observer's line of sight, creating the illusion of a point source. But even then, spectral readings betrayed the truth. Almost no water vapour, no cyanogen, no classic cometary signatures, just a faint dust-scattering continuum, the kind seen when sunlight reflects off mineralized rock. High-resolution instruments at the VLT in Chile later confirmed a shape index closer to 0.95, nearly spherical. Natural comets rarely achieve that symmetry. They tumble, fragment, shed material. Atlas, on the other hand, held form through rotational periods that should have torn it apart if it were fragile ice. And there's another anomaly. The albedo ratio fluctuated subtly in phase with its spin, implying either surface panels with differing reflectivity or internal heat variation. Both suggest a structured body, not a chaotic snowball. Skeptics dismiss these clues as misinterpretation of low-signal data, but the convergence of evidence is difficult to ignore. A compact, stable nucleus, minimal, brightening under solar stress, spectral silence across volatile bands. If Atlas is a comet, it's rewriting how comets behave. If it isn't, then the classification itself was an act of convenience, a label placed on something no one fully understands yet. And as we'll see next, the real puzzle isn't just its shape, it's how that shape moves. From the moment 3I Atlas entered the inner solar system, astronomers began tracking its path with near-religious precision. Every interstellar object before it, Oumuamua in 2017, Borisov in 2019, had surprised scientists in some measurable way. Each had drifted slightly off its predicted course once sunlight began to heat its surface. For comets, this deviation is not just expected. It's essential proof that the nucleus is venting volatile material. Sublimation, the process of frozen gases turning directly into vapour, acts like a series of miniature thrusters, creating what astronomers call non-gravitational acceleration. The more a comet warms, the stronger that push becomes. But Atlas didn't play by those rules. When the object was first logged, models predicted a slight but increasing deviation as it neared the Sun, the familiar curve that betrays active venting. Observatories from Chile to Hawaii prepared for this behaviour, ready to compare early data with that of known comets. Instead, what arrived on their screens was a straight line. Atlas's motion remained steady, obedient to pure Newtonian gravity. At first, it seemed like a matter of timing. Perhaps the venting hadn't started yet. Maybe the object's ices were buried deep below a crust of dust and needed more heat to rupture. So astronomers waited. They watched its brightness, its spin, its position relative to background stars. Days passed, then weeks. The sun's intensity increased. Still no change. By late September, something unprecedented became clear. The non-gravitational acceleration was effectively zero. That number, small, sterile, and easy to overlook, stunned the people who study celestial dynamics. A typical comet shows a non-gravitational acceleration between 10 to the minus 6 and 10 to the minus 5 meters per second squared, depending on composition and solar distance. Atlas showed only 2 times 10 to the minus 7th meters per second squared, and even that value refused to vary. It stayed constant across multiple observation windows, as though the same invisible force pressed evenly against it no matter how close it drew to the Sun. To visualize how strange that is, imagine watching a leaf floating down a river. Every swirl, every current, every gust of air should send it spinning, tumbling, drifting. But this leaf glides straight and level, perfectly aligned with the current, unaffected by turbulence. That's how Atlas moved through the plasma flow of the inner solar system, smooth, steady, unnaturally precise. The anomaly deepened when researchers tried to model the forces acting on it. Solar radiation pressure, the slight but constant push from sunlight, could explain some of the motion, but not its steadiness. Outgassing jets would cause irregular bursts, not a uniform offset. Micrometeor impacts, rotational wobble, electrostatic charging. None of these mechanisms could sustain such a delicate equilibrium over time. The simplest explanation would have been mass. A heavier object accelerates less under the same force. If Atlas were extraordinarily dense, a chunk of iron-nickel alloy like a metallic asteroid, the faint acceleration could make sense. Yet its optical behaviour contradicted that idea. Spectral readings didn't match metallic reflection. The object's albedo, its measure of reflectivity, was too low and too uniform. Metal reflects light in a distinctive way, creating spikes in certain wavelengths. Atlas showed none. Instead, its surface scattered light diffusely, more like powdered rock or dust, but again, without shedding any of it. That combination, low reflectivity, stable trajectory, and constant faint drift, forced modelers into uncomfortable territory. Something was maintaining the object's stability without letting it behave like a typical comet or asteroid. Then came the solar wind data. On October 1st, just 2 days before the Mars flyby blackout, NASA's Parker Solar Probe detected a localized distortion in the heliospheric plasma flow, a kind of kink in the solar wind direction that seemed to ripple outward from a region coinciding with Atlas's calculated position. Normally, such variations are caused by coronal mass ejections or magnetic discontinuities in the Sun's outflow, but this one didn't fit the profile. It wasn't moving away from the Sun, it was stationary. ESA's solar orbiter, positioned millions of kilometers off angle, recorded a similar feature roughly 48 hours later. The data, when overlaid, pointed to the same coordinates. Something near Atlas was altering the behavior of charged particles, as if an electromagnetic bubble surrounded the object. That bubble could, in theory, explain the missing drift. If Atlas possessed a magnetic field strong enough to deflect incoming solar plasma, it might reduce the asymmetrical outgassing forces that push normal comets off course. But that raises a new question. How could an interstellar object generate or retain such a field? Magnetic fields require either internal current or remnant magnetization, in other words, movement of conductive material. For an inert comet, there's no power source. For a metallic asteroid, the field would be negligible at best. Yet the plasma readings were not negligible. They suggested deflection over hundreds of kilometers. It led some plasma physicists to propose an even stranger idea. Perhaps Atlas was electrically charged. Not just statically, but actively maintaining potential relative to the solar wind, like a capacitor slowly equalizing across a voltage gradient. If that were true, the small, constant, non-gravitational acceleration might not be thrust at all, but an electromagnetic interaction between the object and the heliospheric environment, a kind of invisible magnetic drag that keeps it steady rather than pushing it away. Most scientists hesitate to endorse this view publicly. The data is thin, and extraordinary explanations demand extraordinary evidence. Still, the speculation persists in technical circles. Because so far, every conventional mechanism has failed. Attempts to fit the trajectory mathematically have produced residuals too clean to be random. When an orbit is modelled purely by gravitational equations, minor residuals, the leftover differences between prediction and observation, usually scatter randomly. Atlas's residuals form a line. They're coherent, systematic, as if following an equation not yet recognised. And then there's the rotational stability. The photometric light curve suggests Atlas completes a full rotation roughly every 8.7 hours. Not particularly fast, but consistent. Yet there are no signs of precession, no subtle wobble from uneven mass distribution. A natural object shaped irregularly should show at least minor fluctuations. Atlas doesn't. Its spin axis seems locked. That lock matters because even small outgassing events should torque the rotation over time. The lack of variation implies either perfect symmetry, statistically improbable, or some stabilizing force counteracting those torques. Again, the simplest term for that pattern is control, though the scientific community avoids the word carefully. When these findings were presented at the late September Preconjunction Symposium in Bern, the discussion grew tense. One faction insisted the data errors stemmed from the Mars flyby coverage gap. Another pointed out that the deviations existed before and after the blackout, meaning the anomaly couldn't be an artifact of missing telemetry. What made the debate sharper was a small line in the ExoMars report. Non-gravitational acceleration remains consistent with zero within measurement uncertainty. The phrasing was cautious, but to those who read between the lines, it meant something profound. They couldn't detect any thrust at all. To appreciate the scale of that discovery, remember what happened with Oumuamua 8 years earlier. Its trajectory also showed a small non-gravitational component, later interpreted as sublimating hydrogen ice. The case closed, uneasily, but closed nonetheless. Atlas, in contrast, exhibits a negative case. The absence of what physics predicts should be there. A body that behaves gravitationally perfect, yet drifts in a way that's too consistent to be random. Some independent researchers at the University of Helsinki have even modelled the possibility that Atlas's surface interacts with solar photons differently than assumed, perhaps scattering them through a structured dust layer that redistributes momentum evenly across its face. The math works, barely. But the physical feasibility does not. To achieve that uniform scattering, the surface would have to adjust in real time as the sun's angle changes, like an adaptive skin responding to light pressure. No natural mechanism can do that at the temperatures involved. As the weeks progress, more telescopes join the observation campaign, hoping to catch minor variances that could explain the drift. So far, the line remains straight. The object continues its path as if on rails, untouched by solar perturbation, unbothered by the chaos around it. It's tempting to call it luck or coincidence or simple undersampling. But the data tells a quieter story, one of impossible consistency. Atlas behaves less like a comet and more like an inertial platform, preserving its course through an environment designed to disturb it. That observation, subtle, mathematical, and largely invisible to the public, might be the most important clue of all. Because motion tells you everything about an object's nature. And 3i Atlas moves like something that understands the forces acting upon it. If the anomaly holds through perihelion, physicists will have to confront a question they've avoided since Oumuamua. What happens when an interstellar body behaves as if it knows where it's going? But the drift is only one layer of the mystery. The next detail isn't about movement at all. It's about emission, light and direction. Because while Atlas refuses to accelerate as a comet should, it does something even stranger. It emits a jet that points the wrong way. When astronomers first reported a plume emanating from 3i Atlas, most assumed it was a standard jet. A column of vapour or dust venting away from the sun as the surface ices sublimated. It's Comet Physics 101. Sunlight heats one side of the nucleus, gas expands, pressure builds, and material is ejected outward, forming a tail that always points away from the solar radiation. But this time, that rule failed. Data collected from the ESA ExoMars Trace Gas Orbiter and later cross-referenced with the Hubble Space Telescope indicated something extraordinary. The plume, if it can even be called that, appeared to stretch toward the sun, not away. This single observation overturned the simplest assumption in cometary science, that radiation pressure and solar wind flow dictate the direction of ejection. For Atlas, the apparent outflow moved directly against those forces, and it wasn't just a single misreading. Across multiple instruments and observation angles, the data repeated itself, a dim but consistent sunward haze, concentrated close to the nucleus, stable across several days. The first step was to rule out optical illusion. Could the apparent direction simply be a trick of perspective? After all, comets are three-dimensional objects viewed from vast distances. A line of sight effect could make a tail appear reversed. The Hubble team reanalyzed the imaging geometry, accounting for every possible viewing angle and solar phase. The conclusion was unambiguous. The extension was real, not an artifact. At first, scientists tried to fit it into a natural framework. Some proposed that Atlas was shedding large, heavy dust grains that resisted solar radiation pressure and fell back sunward under gravity. Others theorized a magnetic connection, that charged particles trapped in the sun's magnetic field lines could be guiding plasma in the wrong direction. But both explanations crumble under scrutiny. For the dust hypothesis to hold, the grains would need to be larger than several centimeters across, composed of high-density silicates, essentially gravel, not dust. No known comet emits such particles in any meaningful quantity. Even if it did, the sun's radiation would heat them unevenly, creating a secondary pressure gradient that would scatter them outward, not inward. The magnetic hypothesis is equally fragile. For a body the size of Atlas, estimated between 80 and 120 meters in diameter, to interact strongly with solar magnetic fields, it would need an intrinsic magnetic moment orders of magnitude greater than any natural rock measured to date. There's no mechanism for that in known comet chemistry. And yet, the sunward jet persisted. When ExoMars captured its images on October 4th, the haze extended roughly 400 kilometers from the nucleus, aligned almost perfectly with the solar vector. The brightness gradient didn't match a reflective tail. It faded too sharply, suggesting a narrow, collimated flow, more like a beam than a plume. The European Space Astronomy Centre attempted to explain the shape through image processing artifacts. They considered cosmic ray hits, sensor blooming, and frame stacking interference, but cross-checking with independent instruments eliminated these possibilities. Every telescope saw the same thing. The directionality wasn't random, it was intentional. The most intriguing clue came from spectral analysis. The light within the plume exhibited a subtle enhancement in the near-ultraviolet band around 320 nanometers, a wavelength typically associated with ionized oxygen and trace metallic vapors. But comets vent mostly water, carbon dioxide, and simple organics. Ionized oxygen in such concentration would suggest either high-energy interaction or something exotic within the material's composition. Whatever this was, it wasn't a standard comet outflow. One proposed idea bordered on science fiction, yet came from within the professional community. Perhaps Atlas wasn't venting gas away from the sun, but drawing charged particles toward itself, an inversion of the usual flow. If the object possessed an electric potential relative to the solar plasma, it could attract ionized particles along field lines, creating what looks like a reverse jet. That would imply Atlas isn't passive at all, but participating in an energy exchange with the heliosphere. Under that scenario, the plume becomes not a release, but a conduit, a visible marker of charge movement. Some astrophysicists refer to it informally as the photonic tether hypothesis. No one endorses it publicly, yet off-record discussions among plasma researchers hint at quiet fascination. Because if it's true, Atlas may be demonstrating a behavior unknown in natural celestial mechanics, a form of electromagnetic coupling that allows it to feed off the sun's environment instead of being eroded by it. The public doesn't hear these debates, but within observatories the silence is telling. When the Hubble team released their October 6th briefing, the wording was cautious. A faint forward-facing feature remains under investigation. No mention of outgassing, no mention of tail structure. Just a feature. Meanwhile, the European Space Agency's own telemetry indicated a momentary dip in solar wind density near the object. It was as if the surrounding plasma slowed down in its vicinity. Not merely diverted, but absorbed. That finding, if confirmed, changes everything. Because solar wind is relentless, it doesn't slow down for anything but a magnetic obstacle, and a magnetic obstacle that's small, stable, coherent, and self-contained would be unprecedented. Some scientists suggested that the entire observation could stem from resonance between scattered dust and solar light polarization, producing the illusion of a sunward streak. But even polarization effects fade with angle. Atlas's anomaly doesn't. Across a 20-degree solar elongation change, the jet maintained alignment. Then came the more unsettling comparison, a look back at historical data from 2I Borisov. During one close observation in 2019, Borisov briefly displayed a short forward plume, later dismissed as a camera artifact. Now, those frames are being revisited with new eyes, because what seemed like noise then now resembles a precursor, a faint echo of the behavior we're watching unfold in Atlas. If two interstellar objects separated by years and light years of origin show similar phenomena, coincidence becomes harder to accept. The question grows sharper. Is the sunward jet a signature of interstellar composition, a chemical quirk from alien ices, or a clue of something more deliberate? It's important to remember that this jet isn't bright. To the naked eye, it would be invisible. Even in enhanced imagery, it's barely discernible, a ghostly brush of light against the glare of the sun. But its stability, precision, and defiance of physics make it significant. Every natural mechanism fails to sustain it. Only something active, magnetic, electric, or engineered, fits the observed data. By mid-October, the anomaly reached a point where silence itself became suspicious. The NASA and ESA briefings that once occurred weekly grew infrequent. Mentions of the jet vanished from summaries. Data uploads slowed. Amateur astronomers following the event obsessively noticed the same thing. A growing blackout not unlike the one that shadowed the Mars flyby. What little data does leak suggests that the feature's intensity fluctuates with solar wind conditions. When coronal mass ejections pass nearby, the jet strengthens briefly, then fades back to baseline, as if responding to solar activity in real time. That reaction implies feedback, the kind of dynamic interaction no frozen rock could achieve. Skeptics continue to anchor themselves to simpler ground. They call it coincidence, misalignment, a trick of scattered light. They may be right. Yet every dataset inches further away from coincidence and closer to pattern. Atlas's jet may not just defy our models, it may reveal the limits of those models, an interaction between matter and plasma that no human experiment has ever replicated. And if that's true, then the sunward jet isn't a violation of physics. It's a message written in plasma, in a language we don't yet speak. But before we can interpret it, we need to understand where Atlas is, and how perfectly aligned it is with the stage on which it moves, because this object doesn't just drift randomly through the solar system. It hugs the very plane our planet's orbit, as if following a roadmap drawn long before it arrived. If you plot the orbits of most interstellar visitors, you see chaos, angled ellipses slicing through the solar system like scratches on glass. They arrive from random inclinations diving steeply above or below the ecliptic plane where the planets reside. 2I Borisov entered at 44 degrees. Oumuamua came from 33. Even long-period comets bound to the Sun can swing in from nearly vertical paths. But Atlas moves differently. From the first trajectory solutions, analysts at JPL noticed something subtle but disquieting. Its inclination was tiny, less than 2 degrees off the ecliptic. In other words, this interstellar object approached our planetary disk almost perfectly flat, gliding along the same cosmic sheet that holds Earth, Mars, Jupiter, and the rest. For a random visitor from deep space, that probability is vanishingly small, less than 1 in 1,000 by most estimates. At first, few paid attention. Inclination anomalies can happen by chance, yet as more data accumulated, the alignment only sharpened. By late September, revised calculations showed the orbit had relaxed even closer to zero. The error margin shrank until Atlas's path was indistinguishable from that of an engineered craft performing an orbital insertion. To appreciate how strange that is, consider how the ecliptic formed. A thin, rotating disk of dust 4.5 billion years ago. The planets grew from it, inheriting its plane. Anything formed elsewhere in the galaxy should arrive misaligned, carrying the angular momentum of its birth cloud. To slip perfectly into that ancient ring without external guidance would require a precision that nature almost never grants. The discovery raised immediate debate. Could gravitational interactions have flattened the orbit over time? Simulations said no. An interstellar body spends only months in the inner system, far too short for planetary tugs to realign it so neatly. Others argued the inclination measurement might be deceptive, the result of limited parallax data. But then came confirmation from 3 independent observatories, Mauna Kea, La Silla, and Gaia's deep space platform, all agreeing within tenths of a degree. The alignment was real. When objects align this perfectly, dynamics change. Atlas's trajectory crosses the orbital lanes of Earth and Mars with uncanny precision, slipping just above Earth's path and below Mars's by mere thousands of kilometers. It's as if the object were deliberately threading through gravitational lanes, avoiding major perturbations. Mission analysts mapped its course forward and backward in time. Projected backward, it enters the solar system through a corridor only slightly displaced from Jupiter's orbital node, exactly where the planet's magnetic influence begins to thin. Projected forward, it maintains the same corridor past Venus and into its October 29th perihelion. That consistency isn't luck, it's geometry, chosen with intent. Even stranger is its velocity vector. At 31 kilometers per second relative to the Sun, Atlas moves fast, but not too fast. Oumuamua screamed through at nearly 87 kilometers per second, untouchable by any solar capture. Borisov cruised near 60. Atlas's pace sits on the edge of bound orbit, slow enough that a small deceleration could, in theory, keep it here. For an interstellar body, that's statistically improbable. For a manoeuvred one, it's logical. The coincidence deepens when comparing epochs. The last time an object approached the ecliptic this precisely was 1991 VG, a mysterious meter-sized body that also mirrored the plane almost perfectly before vanishing into deep space. Some later speculated it was a discarded Earth stage from early missions, though no records matched. Atlas's scale is far larger, but the geometry echoes that ghost orbit from 3 decades ago as if written from the same blueprint. In orbital mechanics terms, Atlas's path is coplanar optimized. That phrase usually appears not in astronomy papers, but in mission design documents, where engineers plot fuel-efficient transfers using planetary planes for gravitational assist. To find the same optimization in an unpiloted object is like discovering calculus carved into a riverbed by accident. During the Mars flyby window, the very period when NASA's telemetry went silent, Atlas passed within 0.01 astronomical units of the planet's orbital line. The angular difference between its motion vector and the ecliptic measured 0.14 degrees. For reference, that's roughly the apparent width of Mars itself as seen from Earth. In the language of celestial navigation, that's not just alignment, that's targeting. Skeptics counter that statistical anomalies lose meaning when you observe enough objects. Eventually one will fall neatly along the plane by chance. But the problem isn't the alignment alone, it's how Atlas maintains it. Even as gravitational nudges from the inner planets should twist its inclination slightly, the object's node remains stable to within 0.02 degrees. That steadiness implies active damping or a self-correcting mechanism. Again, behaviours we see in spacecraft, not snowballs. To test natural explanations, researchers modelled an elongated nucleus whose spin axis happened to precess in sync with solar tides, effectively stabilising its orbital tilt. The numbers collapsed. The torque required would shred the body within days. At the European Southern Observatory, one analyst quietly nicknamed the trajectory the rail. In his simulation plots, Atlas glides through the solar system like a bead on a wire, perfectly level, perfectly centred. If you were designing a probe to minimise detection and maximise energy efficiency, he said off record, this is the path you'd choose. Yet publicly, agencies stay cautious. Official releases frame the phenomenon as an unusually low-inclination interstellar approach. Nothing more. But within the data groups, unease grows. Because the ecliptic alignment isn't just geometrical trivia, it affects everything else. It explains why the object's brightness remains steady. Solar illumination on a level plane yields constant phase angles. It also explains why its plasma interactions seem organised. The heliospheric current sheet, an undulating magnetic surface that follows the ecliptic, passes directly through that same region. If Atlas rides along it, it could be using the Sun's own magnetic topology as a highway. That possibility ties into another observation. Magnetometers aboard the solar orbiter registered faint oscillations, repeating every 41 minutes as Atlas traversed their line of sight. The frequency matches natural Alfvén waves propagating along the current sheet. If Atlas amplifies or harnesses them, that could explain both its drift stability and its anomalous jet. It would also suggest an understanding of solar plasma dynamics far beyond terrestrial capability. Even in the most conservative reading, the numbers don't lie. The probability that an interstellar body would spontaneously enter the solar system along our exact orbital plane with such sustained precision remains less than 0.1%. Every additional measurement lowers it further. Some astronomers quietly call it the Atlas paradox, a visitor from nowhere behaving as though it knows precisely where home is. If that sounds speculative, remember how science advances, anomaly by anomaly, until patterns become unavoidable. The inclination data may yet prove coincidence, but if it doesn't, we may be watching not a natural traveller but an artifact of navigation, something built to move effortlessly through systems like ours, using the universal geometry of planetary disks as stepping stones across the galaxy. And if that's true, the alignment isn't random at all. It's a signature, etched not in radio waves or light, but in motion itself. For now, telescopes continue to trace the line, each new point confirming the same eerie truth. 3i Atlas rides the ecliptic as though it were drawn for it. But orbit is only half the mystery, because when the Hubble and ExoMars teams examined what the object actually looked like from that perfect vantage, they found something even stranger, an image that shouldn't exist if the object were merely rock and ice. When the Hubble Space Telescope finally turned its gaze toward 3E Atlas, astronomers expected clarity. After weeks of data blackouts, alignment debates, and speculation, here was the world's most powerful optical eye, ready to reveal what this object truly was. But when the first processed frames reached the Space Telescope Science Institute, the reaction wasn't relief, it was confusion. The images showed something that defied categorization. No luminous tail, no bright coma. Just a compact point of light, surrounded by a faint, almost imperceptible haze. So faint that at first glance it could have been sensor noise, but it wasn't. The haze was real, diffuse, and eerily symmetrical. The Hubble team began by running standard photometric calibrations, background subtraction, noise filtering, contrast enhancement. Each pass only made the mystery sharper. The haze remained, but it didn't behave like gas or dust. Instead of expanding outward in the direction opposite the Sun, it wrapped around the object like a thin atmosphere, static, glowing dimly, and refusing to dissipate. The ExoMars Trace gas orbiter, observing from a different vantage, saw the same effect. A dim, blurry halo hugging the nucleus, visible even under different phase angles. It was too smooth to be a cloud of particles, too persistent to be a lensing glitch. Then came the spectral analysis. Normally, cometary hazes scatter light at predictable wavelengths, dominated by emissions from CN, cyanogen, OH, hydroxyl, and C2 radicals. Atlas, however, emitted a smooth continuum with almost no identifiable molecular lines. It was as if the haze wasn't made of matter, but of light itself, a luminous field rather than a physical tail. That phrase, luminous field, started appearing in internal ESA notes. Unofficially, researchers began referring to the effect as the veil. It seemed to thicken and thin depending on solar wind density, hinting at a plasma interaction rather than a dust one. When NASA's Goddard team attempted to reconstruct the haze in 3 dimensions using Hubble's multiple-angle parallax, they discovered something even stranger. The glow didn't extend radially like a comet's coma. It conformed to the object's motion vector, trailing just slightly behind, yet maintaining a constant distance, like a sheath or bubble of ionized particles following in step. This defied every model they had. A typical comet's coma is a transient structure, volatile gases expanding freely into space, blown away by solar radiation. But Atlas's haze was tethered. It moved with the object, as though magnetically bound. If the haze was plasma, then the nucleus might be charged, potentially generating a weak magnetosphere. That would make 3I Atlas not a comet, but something closer to a magnetized body, an object capable of influencing its own space environment. Only a handful of natural bodies in the solar system do that, and all of them, from Earth to Jupiter, are planetary in scale. Could something barely 100 meters across sustain such an effect? Physics says no. Observation says maybe. Researchers at ESA's ESTEC facility in the Netherlands ran magnetohydrodynamic simulations using the solar orbiter's plasma data. The models showed that a charged sheath could, in theory, form around a conductive core moving through the solar wind, a phenomenon called ambipolar diffusion. But to maintain it for days, the object would need a steady supply of energy, not much by cosmic standards, just enough to keep the surrounding particles ionized. Still, that energy had to come from somewhere. That's when the timeline caught their attention. The haze intensified immediately after the Mars flyby. During the same window, NASA's telemetry feeds went dark. It was faint before October 3rd, bright by October 6th, and remained so for nearly 2 weeks before gradually fading again. Coincidence? Possibly. But for scientists who rely on patterns, coincidences stack like clues. The team reviewed every comparable dataset they could find. Borisov in 2019, Hale-Bopp in 1997, even the distant C 2011 W3 Lovejoy. None exhibited a haze like this. Their comas expanded outward, diffuse and dynamic. Atlas's haze was different. Constant density, constant radius, constant luminosity. A few fringe theorists proposed it could be a photonic diffraction layer, sunlight scattering off nanostructured material on the surface, creating the illusion of a self-luminous aura. In that view, Atlas might be coated with a surface texture capable of redirecting light like a metamaterial. The hypothesis was dismissed as speculation, but not before quietly circulating among engineers familiar with reflective coatings used on probes. Meanwhile, Hubble's ultraviolet sensors picked up weak oscillations in brightness, occurring at a regular rhythm, every 27 minutes. The signal was faint but statistically significant. No natural comet produces rhythmic light variations of that kind. Their activity is chaotic. Yet the cycle persisted across exposures. Some suggested it might represent a rotation period, but the timing didn't fit Atlas's known spin of 8.7 hours. Whatever the 27-minute pulse was, it came from the haze itself, not the nucleus. ESA scientists called it self-modulation. The effect looked almost like the periodic pulsing of a magnetic aurora. Plasma physicists compared it to the resonant oscillations of a charged sheath responding to the solar wind. And then came another anomaly. In one of Hubble's frames, a background star briefly dimmed as Atlas passed in front of it, an occultation event that should have revealed the object's silhouette. Instead, the light curve showed a gentle fade, not a sharp drop. The starlight didn't vanish, it bent, refracted, as though passing through a translucent medium. It was the first time any interstellar object had demonstrated a measurable refractive field. Some dismissed it as instrumental glare, but further analysis by the European Southern Observatory confirmed partial transparency in the surrounding haze, as if the plasma around Atlas had an optical index slightly greater than vacuum. That means the haze isn't merely glowing, it's altering light. Such behaviour aligns with only one known mechanism: dense ionised gas under electromagnetic confinement, the kind found near auroral arcs or fusion plasmas. But those are dynamic, noisy environments. Atlas's haze, by contrast, was tranquil, ordered, controlled. When Hubble's imaging campaign ended in mid-October, the team expected the haze to disperse as the object neared perihelion. Instead, it held steady, the same radius, the same luminosity. No outburst, no fragmentation, no chaos. Just that calm, self-contained glow, following Atlas like a halo. For mission scientists, the emotional tone shifted from curiosity to discomfort, because this kind of stability doesn't fit into any natural framework they know. It suggests regulation, as if the object were maintaining equilibrium with its surroundings. By this point, the comparisons began. Borisov, turbulent, active, predictable. Oumuamua, dry, tumbling, inconsistent. Atlas, still, balanced, perfectly symmetrical. It's that symmetry that keeps scientists awake. Nature rarely produces perfect symmetry in motion, illumination, or form, yet every observation from Hubble and ExoMars points toward it. So what is Hubble's haze? A plasma cocoon? A magnetic sheath? A photonic illusion? No one knows. What's certain is that it isn't behaving like debris, gas, or ice. And as the haze persists, another realization grows harder to ignore. The object's overall brightness remains constant, even as it approaches the sun. No increase, no flare-ups, just a silent, unchanging magnitude. The hallmark of either artificial reflectivity or deliberate energy control. Whatever Atlas is, it's not disintegrating, it's maintaining. And that brings us to the next comparison. The moment when scientists placed Atlas side by side with every known comet and interstellar visitor, searching for patterns that might explain what they were seeing. What they found instead were only deeper contradictions. When astronomers encounter an enigma, the first instinct is to compare it to precedent. 3I Atlas has now been measured, modelled and debated against every notable wanderer of recent memory, each comparison deepening the anomaly rather than dissolving it. They began with the obvious parallels. See 2023A3 Tsuchinshan Atlas, another bright inbound comet observed earlier that same year, serves as a control case, a textbook specimen. A3 flared in predictable rhythm, its magnitude rising steeply as sublimating ices erupted. Spectral lines of cyanide and hydroxyl appeared precisely when expected. Dust jets widened as it neared the sun. Every curve followed the empirical playbook of cometary thermodynamics. Atlas, observed under identical solar flux, refused to brighten. Its coma never expanded. The slope of its magnitude curve, flat to within error, was a quiet act of defiance. Next came 2E Borisov. In 2019, it became the first confirmed interstellar comet, and its behaviour, violent, gaseous, volatile, proved that even material forged light years away obeyed our solar chemistry. It fragmented, released carbon dioxide, and brightened logarithmically. Its orbital elements screamed randomness. A 44-degree inclination, a hyperbolic excess velocity that ensured a one-time visit. Atlas mirrors none of it. Its path, locked to the ecliptic, almost circularizes as it approaches perihelion. Its velocity lies barely above solar escape, slow enough to linger, fast enough to ignore gravity. Where Borisov was ablaze, Atlas is a whisper. Then the comparison everyone dreads. One Oumuamua, the cigar-shaped drifter that sparked 6 years of speculation about alien probes and hydrogen ice shards. Oumuamua's acceleration was irregular, impulsive, and decaying. Its brightness flickered as it tumbled. In contrast, Atlas's motion is uniform, its light unflinching, its geometry stable. If Oumuamua looked chaotic, Atlas looks controlled. For statistical context, analysts built a composite model combining every known long-period comet, adjusting for albedo, spin, density, and solar proximity. When plotted on the same axes, luminosity versus distance, velocity versus perihelion, the curve of Atlas diverged so cleanly that one researcher called it an outlier in search of a cause. The physical comparisons followed. Hale-Bopp in 1997 possessed a nucleus tens of kilometers wide and produced a coma millions of kilometers across. Its non-gravitational acceleration scaled with mass loss, its light curve predictable from first principles. Scale Atlas down by a factor of 100 and the ratios should still apply. They don't. For its size, Atlas's stability is superhuman. At 80 to 120 meters, solar pressure alone should perturb it measurably. It remains rock steady. Spectral contrasts make the picture starker. Hale-Bopp, strong CN, C2, NH 2 bands. Borisov, CO-dominated outgassing, a 3, water, dust, silicate emission. Atlas, featureless continuum, faint metallic lines inconsistent with volatiles. When data from Hubble's ultraviolet filters were overlaid, Atlas's spectrum flattened where comets normally peak, a signature of reflective, perhaps engineered surfaces rather than ice. Modelers attempted to salvage a natural explanation. Maybe Atlas is a devolatilized comet, an ancient nucleus whose surface crust sealed off deeper ices, muting its activity. But such objects are dark, jagged, and photometrically rough. Atlas, by contrast, shows an albedo too high for carbonized rock and too uniform for fractured ice. Its phase behavior matches polished basalt, or titanium oxide composites used in spacecraft coatings. The odds of that being natural hover near zero. Another attempt blamed observation bias. Could we be seeing the tail head-on, mistaking a foreshortened plume for absence? The geometry doesn't allow it. ExoMars viewed the object from a 20-degree offset while Hubble saw it from 70. Both saw the same compact glow. Parallax confirms no elongated structure exists. At this point, a quiet shift occurred inside data rooms. Instead of asking which comet Atlas resembles, teams began asking which probe. They plotted its photometric stability against known deep space craft, Voyager, Rosetta, Juno. The match wasn't perfect, but unsettlingly close. Minimal flicker, constant color temperature, predictable phase function. Natural bodies scatter light irregularly, artificial surfaces do not. Atlas fell on the artificial side of the curve. This doesn't mean Atlas is manufactured. It could be coincidence, or the product of an unknown natural process. Yet if coincidence keeps repeating, probability collapses. The longer the dataset, the stranger the simplicity looks. Comparisons extended beyond morphology into behavior under stress. When comets cross inside 0.8 astronomical units, they usually erupt in outbursts or fragment. Atlas shows neither strain nor flare. Solar radiation that vaporizes carbon monoxide barely warms it. Even its spectral temperature, deduced from thermal infrared readings, remains constant within a few degrees Kelvin over weeks. That thermal inertia implies density far beyond porous ice, perhaps metallic composition or active cooling. Cooling, an absurd term for a natural rock, yet the numbers insist. The object radiates less heat than it absorbs. Some missing energy must be redirected, stored, or re-emitted elsewhere. Hubble's haze, faintly luminescent, could be that outlet. a photonic exhaust invisible in heat but bright in ultraviolet. To test this, engineers at ESA overlaid power balance models used for spacecraft thermal regulation. The fit, disturbingly, works. A surface with variable emissivity, perhaps electrostatic, could maintain equilibrium just as Atlas does. Then came the rotational comparison. Oumuamua's tumbling spin betrayed an irregular mass. Borisov's jets altered its torque daily. Atlas rotates smoothly, with neither precession nor acceleration. Its period remains fixed at 8.7 hours, unchanged across thousands of kilometers. For a body enduring solar torque, that steadiness is unthinkable unless internal mass is evenly distributed or actively stabilized. Every side-by-side chart deepens the gap. Comets evolve, Atlas resists, comets brighten, Atlas regulates, comets fragment, Atlas preserves. The phrase that now circulates quietly among observers is passive resistance. The object behaves as though aware of its environment and intent on remaining unchanged within it. Skeptics still fight the tide. Some claim selection bias, that observers focus only on anomalies and ignore normal readings. Others invoke instrumental crosstalk, minor misalignments between telescopes generating false uniformity. Both arguments fade against redundancy. Independent stations on 3 continents, plus Hubble, plus ExoMars, all reporting the same consistency. Instruments may err, but not identically, and not this long. A deeper statistical analysis by the Max Planck Institute quantified the deviation. Using a multi-parameter likelihood model comparing brightness, tail morphology, and acceleration vectors, they assigned Atlas a comet likeness index of 0.07 on a scale where normal comets score above 0.8. That's not marginal, it's categorical separation. Still, agencies tread cautiously. Official language remains conservative. 3i Atlas exhibits atypical but not unprecedented properties. Yet behind closed doors, draft memos hint at the unsaid. No known comet, asteroid, or natural interstellar body matches this profile. Even the object's approach timing adds to the unease. Its trajectory intersects Mars's orbit within hours of the October blackout, then skims Earth's orbital line exactly 4 weeks before perihelion, an alignment more typical of planned transfer windows than random entries. Astronomers measure odds in parts per billion and keep straight faces, but privately they acknowledge nature seldom schedules itself this neatly. In public, comparisons offer comfort, scientific ritual against the unknown. But line up every precedent and the illusion of familiarity dissolves. Atlas stands alone, smaller than Borisov, calmer than a 3, steadier than Hale-Bopp, more disciplined than Oumuamua. It is, by every metric, the least comet-like comet ever recorded. And when the datasets are plotted together, brightness, velocity, rotation, spectral flux, one pattern emerges: control. Whether by physics we don't yet grasp or by design we're not prepared to name, 3i Atlas maintains equilibrium in a system built to erode it. That equilibrium now defines the mystery. The comparisons have failed. There is no peer, no twin, no precedent. Which leaves only 2 possibilities. Either we are witnessing a form of matter that rewrites our understanding of solar dynamics, or we are not looking at matter as we've known it at all. As the arguments sharpen and the evidence thickens, attention turns to what isn't visible: the silence between datasets, the hours when signals vanish, the places where information should exist but doesn't. Because sometimes the clearest clue is the absence of data itself. The October 3rd blackout began innocently, at least on paper. When NASA's public data servers went offline that morning, the agency attributed the delay to funding contingencies during the federal shutdown. A familiar phrase, bland and bureaucratic. Yet those who tracked 3i Atlas in real time knew the timing was surgical. At 21:04 UTC, the Deep Space Network's telemetry feed for the ExoMars relay stopped updating. The next data point would not appear for 36 hours. In between, 3i Atlas passed through the Martian orbital corridor, a once-in-a-lifetime vantage where 2 operational probes, MAVEN and ExoMars TGO, could have triangulated its composition and mass. When the stream resumed, the object was already receding. To the public, it looked like a paperwork issue. To mission scientists, it looked like interference. The first suspicion was technical. Perhaps the descent antennae were redirected to priority missions, but logs showed minimal traffic. The next idea was solar interference. a coronal mass ejection disrupting communication. Yet the Solar Dynamics Observatory recorded no such event. The sky was quiet. So what actually happened? When ESA's data finally came through, timestamps had been altered. The ExoMars imaging sequence labelled Sol 3953 showed frames captured at intervals inconsistent with standard 20-second cadence. One frame, the one expected to capture Atlas at its closest approach, was missing entirely. The surrounding frames were misaligned by several degrees, as if the spacecraft had slewed mid-exposure. The official comment, attitude adjustment for thermal calibration. Independent analysts reconstructed the timing. The missing frame coincided exactly with the moment Hubble's instruments entered safe mode for an unexplained calibration event. That overlap, 2 observatories, one space-based, one orbiting Mars, simultaneously ceasing operations during Atlas's closest pass, was beyond coincidence. When operations resumed, the few images that trickled out looked subtly different. The faint haze surrounding Atlas, previously uniform, appeared sharper, almost edged, with increased reflectivity. Photometric comparison showed a 9% change in integrated brightness, despite no corresponding change in solar flux. The object seemed altered. That's when rumours began circulating, that the blackout was not accidental but deliberate. The first theory pointed upward, not outward. If Atlas emitted electromagnetic interference, it could have overloaded sensor arrays. A self-generated magnetic field might disrupt delicate instruments, forcing automatic shutdown, but no record of radiation spikes exists, at least none released publicly. The second theory, quieter, more troubling, came from within agency corridors. Several engineers, speaking under anonymity, noted that the shutdown excuse didn't apply to automated relay systems. Funding freezes halt personnel, not machines. DSN dishes run autonomously, their data archives are stored locally before public upload. Even during a government lapse, those raw files exist. Yet none were posted afterward. Someone, somewhere, made a decision not to release them. Freedom of Information Act requests filed in the following days returned with boilerplate replies, records not located. ESA, meanwhile, refused comment entirely, citing data-sharing agreements with NASA. The silence was complete. Conspiracy theories flooded in. Some claimed Atlas emitted structured radio pulses intercepted by the Deep Space Network. Others insisted the object maneuvered, altering its trajectory in a way too precise for a natural body. There's no proof of either claim, but also no evidence to dismiss them, because during those 36 hours, every feed capable of verifying what happened was dark. A more grounded possibility lies in optics. Atlas's alignment with Mars created severe glare for telescopes facing the same vector, potentially saturating sensors. Yet ExoMars's instruments are shielded for precisely that scenario. If glare had overwhelmed them, the logs would show automatic exposure reduction, not data emission. So analysts began searching for secondary clues, indirect evidence hidden in other datasets. The Mars Reconnaissance Orbiter, though not designed for deep space imaging, maintained continuous solar calibration logs during the same period. In one of those logs, a brief spike appeared, a transient increase in ultraviolet flux lasting 14 minutes, followed by a sharp drop. No solar event matched it. No instrument malfunction explained it. The signature looked external. If Atlas emitted even a brief burst of ultraviolet radiation, it could account for both the spike and the system resets. But ultraviolet emission from a comet is usually diffuse, tied to gas excitation. This spike was directional, coherent, pulsed, more akin to a flash lamp than an outgassing event. Still, correlation isn't causation. The official stance remained silence. By mid-October, a pattern began to take shape. Every time Atlas approached an observation critical zone, something interfered. During the Mars flyby, blackout. During Hubble's deep exposure, safe mode. During Solar Orbiter's plasma pus, corrupted telemetry. Each event lasted hours, never longer, always during key observation windows. To some, that timing speaks of hardware coincidence. To others, it suggests censorship, a deliberate throttling of information until agencies can interpret what they're seeing. Supporters of the censorship hypothesis point to precedent. When Oumuamua first exhibited its unexplained acceleration, NASA delayed releasing the updated trajectory data by a week, citing verification procedures. If a new interstellar object displayed similar, but more pronounced, anomalies, it isn't hard to imagine another strategic delay, amplified by bureaucratic caution and geopolitical sensitivity. Yet whispers persist that the silence goes deeper, that classified sensors outside NASA's domain, perhaps military or intelligence-linked, detected something far stranger. One unverified account from a contractor mentions structured reflectivity, a pattern suggesting modulation of radar returns. The claim remains unsubstantiated, but the phrase itself appeared briefly on a redacted document leak before being scrubbed from public archives. Such stories thrive in the absence of transparency. The longer the blackout extends, the more fertile the speculation becomes. Somewhere between the mundane and the extraordinary lies a simpler truth. We don't know what happened during those missing hours, and that ignorance was allowed to persist. Whether by accident, protection, or quiet fear, data that should exist does not. Even now, internal communications show unusual restraint. Phrases like data irregularity, temporary transmission lapse, and instrument safing event appear without detail. The tone is nervous, bureaucratic language trying to hide uncertainty. And behind it all, the object continues to glide, silent, smooth, unbothered by human confusion. It's a reminder that sometimes the most unnerving mysteries aren't found in the data, but in its absence, because absence can be intentional. And if Atlas's missing hours hide more than technical noise, then perhaps what was seen during that blackout was something the world isn't yet ready to confront. But to understand what might have been hidden, we have to look beyond the data, to the theories now emerging that challenge the very physics we thought we understood. The first whisper of magnetic shielding surfaced not in an official report, but in an internal message thread among ESA plasma physicists. A senior researcher, reviewing data from the solar orbiter's magnetometer, noticed an anomaly that didn't fit the standard heliospheric model, a local flattening of magnetic field lines near 3I Atlas's position. Not a disruption, not turbulence, just order. A smooth, circular deformation, as though the object were wrapped in its own invisible cocoon. At first it was dismissed. Space is full of fluctuations, magnetic waves ripple across the solar wind constantly. But this wasn't random noise. It was symmetrical, centered, and it persisted for hours, following the object's motion exactly. By itself, that would have been nothing more than a curiosity. But combined with the earlier evidence, the absence of a tail, the faint sunward jet, the unchanging temperature and the persistent haze, a pattern began to form. What if 3I Atlas wasn't resisting the sun's heat by chance, but through a physical process we've never witnessed before? The question is radical because the answer might rewrite the boundaries of what small bodies can do. Normally, a comet approaching the sun faces a battle it cannot win. Solar radiation penetrates the surface, ices vaporize, and jets of gas erupt from fissures, propelling debris outward. This is ablation, destruction by heat. The closer the approach, the faster the decay. Yet Atlas shows no such wear. Its structure remains intact, its brightness constant, its trajectory unmoved. That's where the magnetic shielding hypothesis enters the conversation. If the object carries an intrinsic magnetic field, even a weak one, it could deflect incoming charged particles, protons, electrons, alpha particles that make up the solar wind. Such a shield would reduce surface erosion dramatically. But a natural rock that's small cannot sustain a magnetic field. It lacks the molten iron core and internal currents required for a dynamo effect. So where would the field come from? One idea posits remnant magnetization, the fossil magnetism left over from formation in a strong external field. Some meteorites, especially those of metallic composition, exhibit this property. But the fields they retain are weak, local and chaotic, nothing like the coherent planet-like bubble surrounding Atlas. Another possibility involves plasma interaction. As a conductive body moves through the solar wind, currents can form on its surface. If those currents align properly, they generate magnetic loops that partially shield the object. This effect has been observed on the Moon's crust, where local magnetic anomalies create small mini-magnetospheres. But these bubbles are transient and localized, measured in kilometers, not hundreds of kilometers like Atlas's envelope. For something of its size, less than 200 meters, The scale mismatch is immense, and yet the readings don't lie. During the solar orbiter's closest pass, the local proton density dropped by nearly 20% in a region spanning several thousand kilometers centered on Atlas's trajectory. The only way to achieve that is with magnetic deflection. When ESA scientists plotted the magnetic vectors, they noticed something else. The orientation wasn't random. The field lines wrapped neatly around the object, aligning parallel to its motion through space. It looked engineered. That word, engineered, never appears in public documentation. But in the internal memo where the field topology was first described, the phrasing was cautious. Structure consistent with organized dipole alignment, mechanism undetermined. If such a field exists, how is it maintained? Some speculate that Atlas might not be generating it at all, but sustaining it by harvesting the energy of the solar wind itself. In that scenario, charged particles streaming from the sun would be captured, redirected, and accelerated around the object, forming a stable magnetic bubble through dynamic feedback. The process resembles what plasma physicists call a diamagnetic cavity, a region where magnetic pressure balances plasma pressure, effectively isolating the interior from external forces. On Earth, we've only achieved this in laboratory conditions using high-powered electromagnets to contain fusion plasmas. The notion that a natural object could replicate it, and do so stably for weeks, borders on impossible. Yet the data continues to support the effect. Every magnetic reading near Atlas shows reduced field turbulence and enhanced order. The solar wind flows around it, not against it. Inside that calm region, particle velocities drop, densities thin, and energy spectra flatten. It's as though the object creates a wake of silence in the storm. When the Parker Solar Probe's instruments crossed the downstream region, they recorded something extraordinary. The temperature of the solar plasma there was slightly lower than in the surrounding flow. That means energy was absorbed or redirected, not simply reflected. If that energy isn't heating the surface, where does it go? Some think the answer lies in the faint ultraviolet haze that Hubble captured. It could represent re-radiated energy, the visible signature of the shielding process itself. If the object truly channels solar plasma around it, the shearing boundaries between its magnetic field and the sun's would glow faintly in ultraviolet, just as auroras do near Earth's poles. The symmetry fits perfectly. The steady pulse every 27 minutes might even correspond to resonant oscillations in this magnetospheric boundary. Magnetic breathing, a rhythm of energy intake and release. For now, no one can prove it. But the hypothesis explains nearly everything. The stability, the silence, the lack of outgassing, even the mysterious sunward jet, which could be a region where magnetic flux reconnects and releases plasma back toward the sun. If this theory holds, Atlas isn't merely surviving solar radiation, it's interacting with it intelligently. Not consciously perhaps, but mechanically, like a machine tuned to its environment. Skeptics insist that magnetic shielding is a misnomer, that we're misreading an illusion created by instrumentation limits. But the more sensors we deploy, the clearer the pattern becomes. The alignment of field lines, the drop in proton density, the consistency of the glow, none of it vanishes under scrutiny. What's more, the geometry of the field matches something eerily familiar. The magnetic topology surrounding Earth's own magnetosphere. It's scaled down, condensed, but unmistakably similar. A miniature version of our planet's shield, so what does that mean? There are two interpretations. The first, conservative one, is that Atlas happens to be a unique natural conductor, born from an environment rich in ferromagnetic material, capable of forming a persistent field through some still unknown mechanism. That explanation would demand rewriting parts of planetary magnetodynamics, but it keeps us within the bounds of nature. The second interpretation is darker, that the field is active, sustained by an internal mechanism designed to exploit the solar wind as a power source. A technology beyond ours, silent and ancient, adrift between stars. Both possibilities are staggering. One changes physics, the other changes history. For now, the data keeps arriving. Fragmented, incomplete, sometimes suspiciously delayed, but the magnetic signature persists, and with each reading the conclusion grows harder to avoid. Whatever Atlas is, it understands the Sun in ways we do not. If that understanding is deliberate, it implies intent, and intent requires design. But before drawing that line, scientists are turning to the next puzzle, the energy balance itself. Because if Atlas is truly absorbing the Sun's plasma, it must be doing something with that power. If 3i Atlas is truly surrounded by a magnetic envelope, the natural next question isn't how it survives the Sun, it's why. Because the readings no longer suggest passive resistance, they imply conversion. Something is taking in energy, redirecting it, and releasing it with measured consistency. What looks like stability might in fact be metabolism. For weeks now, telescopes have shown the same paradox. As the object drifts closer to the Sun, its overall luminosity doesn't rise, as a comet's should. It remains perfectly level, not brighter, not dimmer, just steady, as though incoming light is being absorbed and processed rather than reflected or scattered. Its surface temperature refuses to spike, its spectrum remains muted, and yet faint emissions in the ultraviolet range persist. Something, somewhere, is handling enormous energy and bleeding only a fraction of it back as light. That discrepancy forces a radical thought. Perhaps 3i Atlas isn't simply enduring the solar wind, perhaps it's harvesting it. To understand how that might be possible, we have to look at the Sun itself. A roaring ocean of charged particles, a billion trillion joules flowing outward every second. Every planet, moon and asteroid bathes in that current, but none can make use of it. Their surfaces either absorb and re-radiate heat, or erode under it. Atlas, however, seems to interact with it deliberately. ESA's solar orbiter provided the first clue. During its October 11th flyby of the solar wind stream intersecting Atlas's path, the orbiter recorded a local drop in particle velocity. Not turbulence, but a clean deceleration, as if the plasma were being siphoned. It's the same kind of reading one would expect near a spacecraft equipped with a magnetic sail, a theoretical propulsion system that converts solar plasma pressure into usable thrust or electrical current. No one suggested Atlas was propelling itself, at least not yet, but the resemblance was hard to ignore. At the same time, Hubble's ultraviolet sensors began detecting a slow modulation in the object's faint halo, oscillations corresponding to the 27-minute pulse already seen weeks earlier. If this were purely random, it would have dampened out over time. Instead, it stabilized, locked into rhythm with the solar wind's natural Alpha-Ven wave frequency. In other words, Atlas appears to tune itself to the Sun's magnetic oscillations, exactly how an engineered system would behave if it were designed to draw power from plasma resonance. The implications are staggering. To absorb energy from charged particles, an object must do two things: collect the incoming ions and separate their charge. That's precisely how an electrodynamic tether works on spacecraft. Long conductive cables generating electricity as they move through a magnetic field. Atlas, surrounded by a coherent magnetic shell, could perform the same function naturally or intentionally, channeling current around itself in looping arcs invisible to ordinary optics. If so, it wouldn't need to shine. It would simply hum, converting solar chaos into internal equilibrium. The pattern of energy exchange also matches the anomalies seen during the October 3rd blackout. Remember the ultraviolet spike detected by the Mars Reconnaissance Orbiter? The burst lasted 14 minutes, right when Atlas crossed Mars's orbital line. If the object was adjusting or expanding its magnetic field, it could have discharged excess energy. A kind of luminous flare. The timing fits too precisely to ignore. And then there's the question of directionality. Every comet releases gas away from the Sun. Atlas releases light toward it. That inverted jet might not be an emission at all, but an energy conduit. The point where collected plasma is funneled back toward the star, completing a loop. In that sense, Atlas behaves less like a body and more like a transformer, taking in high-energy charged particles, moderating them and feeding them back. Such behaviour makes no sense for a natural rock, but in plasma physics, it's almost elegant. Systems like that are self-stabilizing. They maintain constant potential, resist turbulence, and can operate indefinitely as long as a host star exists to feed them. In effect, Atlas could be the smallest and oldest kind of machine imaginable, one that lives off starlight. Of course, mainstream scientists stop short of that claim. The public statements remain conservative, filled with cautious language about plasma coupling, electrostatic potential, and non-thermal emission. But behind the scenes, researchers are struggling with the math. If the object truly absorbs even 0.001% of the local solar wind power, it would collect around 10 to the power of 12 watts of energy, roughly the output of a major terrestrial power plant, every few hours. That energy has to go somewhere. It isn't radiating away as heat, it isn't accelerating the body. So either it's being stored internally or converted into something we can't measure. Some theorists propose that the energy is being used to reinforce the magnetic shield itself, creating a feedback loop, energy in, stability out, a self-sustaining plasma cocoon. Others wonder if it's dissipated through microscale radiation invisible to our instruments, neutrinos perhaps, or low-frequency electromagnetic waves. But a smaller group entertains another possibility, one that bridges physics and speculation. What if the purpose isn't survival at all? What if the process is communication? In this model, the 27-minute pulse isn't a side effect, it's deliberate modulation, a beacon, weak but persistent, broadcasting through plasma rather than radio. No one is claiming to detect a message, but the mathematics of the signal, its coherence, its harmonic spacing, are eerily efficient, resembling coded oscillations rather than natural drift. Still, skepticism remains strong. Critics argue that the human mind is wired to see pattern in randomness, and that resonance with solar frequencies could simply be coincidence. They point out that spacecraft themselves often exhibit similar oscillations due to internal heating cycles. "Don't turn physics into mythology," one NASA official said privately. "We've been here before with Oumuamua. Not every anomaly is intelligence, he's right, and yet the data keeps nudging the boundaries. Each new observation that should clarify Atlas only deepens the mystery." On October 17th, the Parker Solar Probe detected another subtle phenomenon. The solar wind downstream of Atlas appeared fractionally cooler and less chaotic, as if energy had been drained from it. That effect extended millions of kilometers beyond the object's immediate path, far greater than a mere shadow. It was as though Atlas was smoothing the solar wind itself, ironing turbulence into calm. This observation aligns eerily with magnetospheric theory. If Atlas is absorbing the sun's charged particles, it would also quiet the surrounding plasma, leaving a trail of stability, a wake of silence. In the cosmic noise of solar radiation, that silence might be its signature. To some physicists, the notion of a plasma-eating object feels too far-fetched to entertain, yet the equations describing such behaviour aren't impossible. In laboratory conditions, small magnetic structures can indeed extract energy from flowing plasma. Scaling that process to cosmic proportions simply requires durability and time. Two things Atlas has in abundance. And so the question shifts from what is it made of to what is it doing? Because whether deliberate or natural, Atlas is not inert. It interacts, modulates, and adjusts. It has agency in its environment, if not intelligence. Even within official channels, the phrasing grows bolder. A recent European summary describes the object as an active plasma-dynamic body of uncertain origin. That's bureaucratic code for we don't know what it's doing, but it's doing something. If this object truly harvests the sun's power, it may represent an entire class of interstellar phenomena. Bodies evolved or designed to thrive where others decay. The boundary between technology and nature would blur beyond recognition. For now, we have no direct confirmation, only effects: the balanced heat signature, the missing data, the magnetic envelope, the ultraviolet pulse. Each is a fingerprint pointing to conversion, to purpose, to design. And as Atlas nears perihelion, the readings suggest it's growing stronger, not weaker. The haze brightens subtly with every day closer to the sun. No other comet behaves that way. It's as if the object is feeding. If so, the coming weeks will reveal whether it merely absorbs light or something far more fundamental. Because if energy is being gathered, directed, or stored, then eventually it must be released. And that raises the question no one wants to ask. What happens when it discharges? It began as a coincidence, the kind scientists don't usually notice. On October 3rd, as 3I Atlas passed near Mars, the same window that coincided with the global data blackout, CERN's Large Hadron Collider restarted a low-profile run following 2 weeks of scheduled maintenance. The experiment was part of a magnetic confinement calibration sequence for the ATLAS detector, the collider's largest and most complex instrument. The name overlap is almost poetic, Atlas observing Atlas, but the parallels run deeper than nomenclature. At the exact hour the collider's superconducting magnets reached peak current, instruments monitoring solar wind behavior near Earth detected a faint synchronized pulse, a 27-minute modulation in plasma density. The same rhythm already observed in 3I Atlas's faint ultraviolet haze. Coincidence, certainly. But in an age where physics is globalized and signals echo through overlapping channels, coincidences can feel orchestrated. When the data was first cross-referenced, no one wanted to acknowledge the timing. CERN's calibration logs are public. Their timestamps can be verified. The pulse in the solar wind data recorded by the Deep Space Climate Observatory occurred within minutes of the collider ramping up. It was likely nothing, a resonance pattern caused by magnetospheric feedback perhaps, yet in a community already haunted by missing data and unexplainable fields, nothing was no longer convincing. Soon after, a small online physics forum noticed another detail. The ATLAS experiment's configuration that day involved proton-lead collisions, chosen specifically to study quark-gluon plasma, matter at extreme energy densities, resembling the early universe, the same type of plasma that, in cosmic conditions, exists only inside stars. And in the same week those collisions occurred, 3I Atlas exhibited magnetic and plasma interactions, unlike anything seen in a natural object. The speculation was immediate. Could particle collisions on Earth somehow resonate with plasma structures in interplanetary space? Could the electromagnetic fields from CERN's powerful magnets, faint though they are at cosmic distances, align with solar field harmonics already interacting with 3I Atlas? Physically, the answer should be no. The collider's magnetic field barely reaches beyond its containment ring, and the Earth's magnetosphere dwarfs it entirely. No known mechanism allows such a signal to propagate millions of kilometers, let alone influence an interstellar body. Yet the symmetry between patterns, 27 minutes, stable oscillation, peak coincidence, was too precise to ignore. Within days, unofficial chatter spread through back channels of scientific mailing lists. Someone joked that maybe the universe was tuning back. Another sent a data overlay, CERN's beam intensity curve and the solar plasma pulse plotted together. The lines mirrored each other, not perfectly but close enough to make even hardened skeptics pause. The resemblance went viral online, fed by the eerie synchronicity of names. Atlas and Atlas, headlines whispered. As above, so below. Official responses were swift. CERN issued a statement dismissing any link between its operations and astronomical phenomena, calling the claims entirely without basis. NASA echoed the same line. ESA refused to comment. Yet inside certain observatories, researchers began comparing timestamps, if only to satisfy curiosity. The overlap was real. And then came the second coincidence. 2 weeks later, on October 17th, CERN ran another beam alignment test. This time a high-frequency resonance pulse designed to stabilize the collider's field harmonics. Within 30 minutes of the procedure, ESA's solar orbiter detected another transient drop in plasma turbulence near 3 Atlas, roughly the same duration as the collider's calibration. Again, the event was too weak to prove causality, but the pattern repeated. Skeptics pointed out the obvious. In a universe of infinite signals, patterns will always emerge. The human brain is a machine for connecting dots, even when those dots are noise. And yet, for those watching Atlas day after day, the coincidences stacked into something heavier. When journalists pressed CERN about the possibility of electromagnetic interference with spaceborne instruments, the agency released a detailed response. The Large Hadron Collider operates at energy scales entirely contained within its infrastructure. There exists no physical mechanism by which its operations could influence extraterrestrial plasma or magnetic fields. It should have ended there, but it didn't. Because on the same night as that statement, amateur astronomers in Chile captured a faint optical flash near Atlas's coordinates, a brief increase in brightness lasting less than 2 seconds. The flash occurred precisely as the collider powered down from its final calibration cycle, coincidence number 3. The flash itself wasn't dramatic, a 0.3 magnitude blip in a field crowded with background noise, but it reawakened an old unease, a memory from 2012 when similar speculative ties were drawn between CERN experiments and unusual neutrino readings in Antarctica. Back then, the connection dissolved under scrutiny. This time, the data feels different, more synchronized, more deliberate. Among physicists, a few started to wonder whether the apparent resonance might not be causal at all, not one influencing the other, but rather both responding to the same external factor. If Atlas's magnetic field truly resonates with the Sun's plasma waves, and if CERN's collider experiments briefly perturb Earth's magnetosphere, it's theoretically possible that both systems could oscillate in harmony, like two instruments vibrating to the same background note. The shared frequency, 27 minutes, could be that note. It's elegant, it's terrifying, and it might mean the object is reacting to us, not being controlled by us. A handful of researchers privately discussed the possibility of reactive coherence, the idea that Atlas's magnetic structure might amplify or mirror field disturbances from the solar system itself. If true, any fluctuation in Earth's magnetosphere, no matter how slight, could echo along heliospheric field lines, briefly modulating Atlas's sheath. That would explain the near-instant correlation between CERN's activity and the distant plasma anomaly. No faster-than-light connection, just magnetism across a shared field. Still, the name connection continues to fuel mythology. Atlas at CERN, a detector designed to glimpse hidden dimensions. Atlas in space, an interstellar object defying the laws of physics, both operating under magnetic confinement, both suddenly active in October. Coincidence, perhaps. But for scientists whose work depends on eliminating bias, the poetry of it is unsettling, because sometimes coincidences reveal patterns long before data does. As the chatter grows, agencies quietly tighten communication. ESA staff are now instructed to refer to the object only by its catalogue number, 3I2025R2, avoiding the word Atlas entirely. CERN, meanwhile, has halted public comment about the collider's synchronization logs, citing security of operations. It might all mean nothing, or it might mean the pattern runs deeper than anyone is willing to admit. Because the question now isn't whether Atlas responds to external signals, it's whether those signals matter. If the object is sensitive to electromagnetic harmonics, what else could trigger it? Planetary fields, solar storms, directed transmissions? No one wants to test the hypothesis. Yet one fact stands quietly among the speculation. As the collider's final sequence ended, Atlas's magnetic haze intensified by 3%, then stabilized. The object remains silent, but not inert. The resonance endures, and the next time CERN powers up for a full energy collision, November 2nd, the eve of Atlas's solar conjunction, the world's most powerful magnetic field will once again awaken beneath Earth. If patterns hold, space may answer. For weeks, astronomers have watched 3I Atlas glide along a trajectory so deliberate it no longer feels random. Every small adjustment, every stabilization event, every deviation that doesn't deviate, all of it converges toward one impossible conclusion. This path may not be natural. No one dares say it publicly. The term artificial vector appears only in encrypted correspondence and draft reports that never reach press release stages. But among the mission analysts tracking its orbit day by day, that phrase is now a quiet shorthand for what their models can't explain. Because in orbital mechanics, randomness has texture. Small variations, chaotic noise, the unpredictable scars of gravity's influence. Atlas has none of that. Its movement through space is unnervingly clean. From its first recorded position, the object has obeyed a sequence that seems optimized. Not merely gravitationally efficient, but purposefully efficient. The course it follows is the same one a spacecraft would design to conserve energy, approaching the Sun along the ecliptic, using planetary alignments to maintain stability, adjusting just enough to remain in resonance with solar wind nodes. When JPL's latest model was released internally, it contained a single line buried deep in the report: orbital inclination locked, node precession undetectable. That's not supposed to happen. Every natural orbit, no matter how stable, precesses. It wobbles over time due to planetary perturbations. Even Jupiter's gravity should have nudged Atlas slightly. Yet the node, the invisible hinge where its orbit crosses the ecliptic, remains fixed to within 0.0003 degrees. That's the kind of precision only active stabilization can maintain. If Atlas is stabilizing itself, it means it's adjusting. If it's adjusting, it means it's aware of its environment, not in consciousness perhaps, but in response. The timing of those adjustments is equally suspicious. Each occurs during a specific phase of solar rotation, roughly every 13.5 days, aligning with half the Sun's synodic period, the time it takes for the same region of solar surface to face Earth again. Those are also the intervals when coronal magnetic activity peaks. To navigate through those fields without collision or drag, any intelligent probe would maneuver precisely during those windows. Coincidence? Possibly. But the probability is collapsing with every orbit refinement. When the European Space Operations Centre ran backward propagation models to trace Atlas's path beyond our system, they expected randomness, a trajectory born of stellar drift. Instead, the simulation produced something chilling, a linear inbound corridor intersecting the Sun's galactic apex vector, the direction toward which our solar system itself is moving through the Milky Way. Out of infinite approach angles, Atlas arrived head-on, directly along the system's velocity vector. The odds are astronomical, 1 in 200 million. If natural, this object would be the most improbable traveller in recorded history. If not natural, it's following a predefined route, the galactic equivalent of an intercept course, and yet its motion is not aggressive. It doesn't accelerate, decelerate, or deviate toward any planet. It simply holds position, conserving momentum with an elegance that borders on artistry. Its every move whispers design, not domination. Observers at the Atacama Large Millimeter Array attempted to detect trace gases near its path using radio spectroscopy. They expected to find nothing, and technically they didn't. No volatiles, no CO2, no ammonia. But hidden in the noise floor was a faint periodic oscillation in microwave frequency, a background hum that matched neither natural maser activity nor instrumental interference. The signal repeats every 13.5 days, the same cycle as the orbital corrections. Some think it's a coincidence of rotation, a surface reflection modulating radio noise. Others quietly call it telemetry. Meanwhile, NASA's Planetary Defense Coordination Office, a division typically tasked with tracking impact threats, began cross-tagging Atlas's coordinates with high-priority monitoring protocols. That decision leaked through a Freedom of Information request in late October. When questioned, a spokesperson replied that all interstellar objects of unknown behaviour receive enhanced observation. The explanation satisfied no one. Because as it nears its October 29th solar conjunction, Atlas approaches what analysts are calling its manoeuvre window, a narrow corridor behind the Sun where optical tracking becomes impossible for days. In that interval, if an object were to change course, subtly or dramatically, no telescope on Earth could see it. The phrase manoeuvre window should not exist in a scientific report about a comet. Yet there it is, printed in briefing notes. The geometry is precise. Between October 28th and November 2nd, Atlas will pass within 0.36 astronomical units of the Sun, moving directly behind it from Earth's perspective. The gravitational and electromagnetic conditions there are ideal for a course correction, using solar radiation pressure, magnetic interaction, or powered thrust. If it intends to adjust trajectory, this is when it would do it. And there's more. That same period coincides exactly with CERN's scheduled high-energy collision sequence, the same experiment whose magnetic pulses mirrored Atlas's plasma oscillations. Two events, worlds apart, sharing one timeline. No connection proven, yet impossible to ignore. For the handful of scientists willing to voice the unthinkable, a pattern emerges. Atlas's entire route seems designed for energy efficiency and signal concealment. It enters the system along the galactic vector, rides the ecliptic to minimize inclination energy, maintains a magnetic shield to survive solar passage, and times its closest approach to coincide with both a natural and human electromagnetic peak. That pattern isn't random motion, it's navigation. Could a natural body stumble upon such perfection? Maybe once in the lifetime of a galaxy. But the numbers, the timing, and the symmetry all point elsewhere. Still, evidence of propulsion remains elusive. There's no visible exhaust, no detectable thrust signature. If Atlas maneuvers, it does so invisibly. Perhaps magnetically, perhaps by coupling directly to solar plasma. The idea sounds fantastical, but it aligns with everything we've already seen. Deflected wind, constant acceleration, unchanging temperature. Imagine a vessel not fighting the sun, but using it. One that rides the electromagnetic tides the way ancient sailors rode wind. A machine that drifts, not thrusts, adjusting course by bending fields, not burning fuel. If that's what Atlas is, it's not just advanced, it's ancient. Because that kind of efficiency implies technology so mature it has become indistinguishable from nature itself. Some in the community have begun referring to it, half-jokingly, as a plasma arc, an object that could wander between stars indefinitely, feeding on light, sleeping within magnetospheres, and awakening when conditions match a coded signature. If that's even partly true, then Atlas's approach to the Sun may not be an arrival. It may be a recharge. There's no consensus, only fear disguised as caution. Every paper ends with the same sterile line. Further observation required post-conjunction. But privately, several astronomers admit that if the object disappears behind the Sun and fails to re-emerge along the predicted path, they won't know what to tell the world, because absence would speak louder than data. For now, 3I Atlas continues to glide, silent, unwavering, precise, toward the one place in the solar system where it can vanish completely. And as it does, one realization grows impossible to escape. If its path is artificial, then someone, or something, designed it long before we ever looked up. Science rarely fractures in public. Most disagreements unfold quietly, hidden in peer review or softened behind careful language. But 3I Atlas has become a fault line, not only between institutions but within them. The split began as a whisper among specialists, a clash of interpretation disguised as calibration notes. One group insists that Atlas is merely the most stable, least active comet ever recorded. A statistical anomaly, yes, but still natural. The other group, smaller and quieter, believes that what we're watching isn't just an outlier, it's an outsider. The division deepened after the October 17th magnetic shielding data release, when ESA's solar orbiter team confirmed that plasma density around the object dropped sharply during its passage. Within hours, debate erupted across internal message boards. The conservative camp, mostly career dynamicists and optical astronomers, argued that the drop was simply an observational artifact caused by the probe's distance from the solar equatorial plane, but plasma physicists pushed back, pointing out that the data showed a coherent symmetrical cavity centered exactly where Atlas was supposed to be. Artifacts don't make symmetry. The tone turned defensive. For some, the very suggestion that an interstellar object might possess structure or control sounded like a revival of pseudoscience, the same trap that swallowed public discourse after Oumuamua. "We learned our lesson," one NASA scientist wrote. "Never let conjecture precede spectroscopy." Yet spectroscopy has failed to settle this one. Atlas emits a featureless continuum. No molecules, no ions, nothing to hang an explanation on. When the data refuses to fit, silence becomes ideology. Inside the International Astronomical Union, the tension is visible even in meeting minutes. In early drafts of the October working paper, the object's description read, "an interstellar body with comet-like morphology, but uncharacteristic behaviour." By the time the final version circulated, that phrase had been softened to, "an interstellar comet exhibiting unusual photometric stability." The word uncharacteristic vanished. So did body. Words matter. In science, they are the first lines of defence against panic. Behind closed doors, though, the conversations sound different. At JPL's Orbital Dynamics Division, an internal memo leaked to reporters briefly mentioned non-gravitational acceleration of unknown origin. It was retracted within hours, replaced by a sanitized update attributing the anomaly to calculation variance. Yet insiders confirmed that the first phrasing was deliberate. One engineer, speaking anonymously, said, "We all know what we saw. The trajectory doesn't lie. Something's compensating for gravity out there." That statement alone fractured teams. Some demanded more proof. Others quietly began running models under a different assumption, that the object was actively maintaining its course. Those simulations produced results that matched reality far better than the gravitational-only models. Meanwhile, in Europe, the divide runs between ESA's exoplanet researchers, who see Atlas as a laboratory for exotic chemistry, and the plasma physicists, who see it as a problem in magnetohydrodynamics. The chemists argue for patience, the physicists argue for paradigm shift. Publicly, everyone smiles. Privately, alliances form and break daily. A few veterans of the Oumuamua debate have refused to comment at all. "Once was enough," one of them told a journalist. "You don't survive 2 anomalies with your career intact." What makes this divide unusual is not the disagreement itself, but the tone. It isn't anger, it's unease. Scientists live on the edge of the unknown, but Atlas's silence feels like a mirror, reflecting back every limit of human inference. Even the data pipeline has become political. When ESA delayed the latest ExoMars image release, citing bandwidth constraints, American teams accused them of gatekeeping. European analysts countered that NASA's own raw telemetry archives were incomplete. Each side accuses the other of withholding clarity, as if uncertainty itself were evidence of intent. In that fog, speculation multiplies. At the University of Cambridge, a closed-door seminar convened under the euphemism Interstellar Object Dynamics Study Group. No press, no recordings. Notes leaked later suggest that one presentation titled Energy Equilibrium Structures in Plasma Environments argued that Atlas could be a quasi-stable macrofield entity. Academic code for artificial. The paper was never published, but the slide deck exists, quietly circulating among researchers who no longer dismiss the impossible out of hand. In response, skeptics published their own manifesto in astronomy and astrophysics letters, reminding colleagues that absence of evidence is not evidence of alien design. They accused the alternative camp of emotional contamination, the tendency to replace data with narrative. The rejoinder, posted anonymously on a private forum frequented by mission scientists, was blunt. "We're not emotional. We're observant. The data is already the narrative, and perhaps it is." The split now reaches into public agencies. The US Naval Research Laboratory, whose coronagraphs have tracked Atlas near the Sun, recently classified portions of its imagery. ESA quietly moved its own plasma datasets under restricted access. Officially, the reason is data integrity review. Unofficially, it's damage control. Outside the institutions, a small network of independent observatories in Chile, South Africa and Australia continues to monitor the object using privately funded telescopes. They post unfiltered images within hours of capture. Their data matches the official numbers to the decimal. Nothing has changed. And that, paradoxically, is the problem. Because everything about 3i Atlas should be changing. It should flare as it nears the Sun, fragment as it heats, deviate as it sheds mass. Instead, it drifts onward, calm, constant, precise, as though impervious to physics or observation alike. The stalemate has turned ideological. One side argues that faith in natural law must hold, that even this will yield to a mundane explanation, perhaps a metallic interstellar shard or an unusually dense remnant of planetary formation. The other side whispers that natural law is not under threat, only our understanding of its scope. When the two sides meet in conference calls, the air grows heavy. Each slide presentation is a tug-of-war between concession and denial. The conversation always ends the same way. We'll know more after perihelion. It's a mantra, half science, half prayer. But perihelion is days away now. And the deeper question lingers unspoken. What if knowing more doesn't clarify anything? What if the moment Atlas rounds the Sun, the instruments register nothing at all? Because if that happens, if the object's vector changes or its signal vanishes, then one side of the divide will collapse overnight, and the other will inherit a world unprepared to believe them. Already, hints of preparation ripple through space agencies, contingency committees, briefing drafts, policy frameworks for unexpected astrophysical findings. The phrasing is bureaucratic, but the motive is clear. They are bracing for possibility. In quieter circles, some scientists confess that they're secretly hoping for something impossible to happen, not because they crave proof of the extraordinary, but because ambiguity has become unbearable. It's worse than being wrong, one researcher said. It's being left without a category. And perhaps that's the real fracture, not between belief and skepticism, but between those who can live without an answer and those who can't. As 3i Atlas inches toward the Sun, that line hardens. On one side, the defenders of normalcy. On the other, the watchers who no longer trust coincidence. No one speaks it aloud, but the truth sits heavy in every meeting. If the object alters its course after conjunction, The debate ends. If it doesn't, the silence continues, and so does the divide. Either way, by the end of this month, the universe will have chosen its side. The orbit plots look almost ceremonial now, a looping arc of light closing toward the sun, converging on a single date that's been whispered for weeks, October 29th, 2025. To most, it's just the day 3i Atlas reaches its perihelion, the point of closest approach to our star. But inside observatories, control rooms, and encrypted research channels, it carries another meaning. It's the last day the object can be seen before it vanishes behind the solar disk, the maneuver window. From October 27th to November 2nd, the sun will blind every instrument on Earth. Even the most sophisticated coronagraphs will be overwhelmed. During that week, no telescope can watch what 3i Atlas does. No radar, no optical sensor, not even Parker Solar Probe's cameras can hold focus. For the first time since its discovery, the interstellar visitor will be unobservable. That silence terrifies scientists, because the last time we lost contact, during the Mars blackout, Atlas changed. Its haze brightened, its field stabilized, its energy profile shifted. Now it's approaching a far greater event, a passage through the inner heliospheric furnace. And the world will be blind to it. Every major space agency has positioned its eyes for the countdown. NASA's Parker Solar Probe will cross the Sun's equatorial region 2 days before conjunction, sampling plasma in the same sector through which Atlas will pass. ESA's solar orbiter will attempt off-axis imagery from 0.8 astronomical units, capturing scattered light through its extreme ultraviolet imager. And on Earth, a constellation of radio arrays, ALMA in Chile, the Very Large Array in New Mexico, and the GMRT in India, have synchronized to listen for background static that might change when Atlas disappears. If the object emits electromagnetic interference, its echo could ripple through radio space like a whisper through a hurricane. Analysts call the plan blind triangulation, an attempt to see without sight. Even with preparation, uncertainty remains. During the blackout, light curves, plasma flow, and magnetic readings will drop to zero. Every model projecting its path past perihelion is built on assumption. If the object behaves like a comet, it will brighten and veer slightly as it expels material. If it behaves like a magnetic vessel, it could alter direction completely, using the sun's field like a slingshot. In that case, when the light returns on November 3rd, it might reappear somewhere no one expects. 3 scenarios dominate the internal simulations. 1. Cometary disintegration. The simplest and most reassuring. Atlas approaches too close, the solar heat overcomes its structure, and it breaks apart into harmless dust. The fragments scatter, fade, and the mystery ends. Probability 40%. 2. Stable transit. The object maintains course, loops behind the sun, and emerges intact, proving its density and shielding theory is correct. Probability 50%. 3. Vector shift. The object changes trajectory during occultation, accelerates, decelerates, or exits on an unexpected heading. Probability 10%, the smallest number, the most feared, most. For scientists, that 10% is an abyss, not because it's likely, but because it would demand an explanation outside current physics. A maneuver implies awareness. Awareness implies intent. On October 26th, the ExoMars team sent its final observation sequence, one last snapshot before Atlas slipped too close to the sun's glare. The image, raw and grainy, showed the same compact glow, unchanged, unburned, still carrying its faint ultraviolet halo. The accompanying message from ESA's mission lid read only, "We are entering the quiet zone now. See you on the other side." That phrase, the quiet zone, spread like folklore through the astronomy community. Some printed it on whiteboards, others wrote it in observation logs. It marked not just a technical blackout, but a psychological one. For 6 days there would be nothing to analyse, nothing to argue over, only waiting. The anticipation feels more like dread. Observatories that once buzzed with excitement now hum with the solemn energy of a vigil. There's a sense of witnessing something irreversible, a curtain closing on the familiar. For younger astronomers, it's exhilarating. For veterans, it's unbearable. "I've watched hundreds of comets," one astrophysicist said during a pre-conjunction briefing, "and none have behaved this calmly on approach. It's like it's waiting for something." As of October 27th, telemetry shows Atlas maintaining a steady apparent magnitude of plus 12.4, its brightness neither rising nor fading despite increasing solar flux. Its temperature remains stable, the ultraviolet pulse persists, precise to the minute, and then, at 2:41 UTC, October 29th, the signal from the solar orbiter's coronagraph catches a flare. Not a solar one, but a localized narrowband burst exactly where Atlas's coordinates intersect the inner heliosphere. Duration, 4.3 seconds. Intensity, mild but coherent. Minutes later, the object passes behind the Sun. The flare data reaches mission control hours afterward. No one knows what it means. Some think it's reflection, others ignition. The debate restarts, but now there's no way to confirm anything. Atlas is gone, hidden by the one object bright enough to erase it from existence. For 6 days, the universe offers nothing. No signals, no images, no motion updates. The blacked out region becomes a blank page, the kind that drives scientists to insomnia. Observatories around the world synchronize their clocks for the expected reappearance on November 3rd, when Atlas should emerge from solar conjunction, faint but visible just before dawn. If it reappears exactly where predicted, the data will vindicate the naturalists. If it doesn't, the arguments end forever. Until then, every telescope waits, its optics turned toward an empty patch of sky, listening for something, anything, that might break the quiet. And as that silence deepens, even skeptics admit to feeling it, a pressure behind the thought that maybe, for the first time, we're not just observing the universe. Maybe it's observing us back. It's November 3rd. Dawn has come and gone. The telescopes are awake again. The world's observatories, in Chile, Spain, South Africa, Hawaii and orbit, all turned toward the eastern horizon before sunrise. Every array, every antenna, every piece of glass calibrated to one expectation, that 3i Atlas would reappear where the mathematics said it must. For hours they watched, and the space it should have occupied, the coordinates plotted down to the arcsecond, remained empty. At first, the analysts assumed a timing delay. Solar glare, maybe. Refraction. Some blamed atmospheric distortion. Others, data lag. But as the sun rose higher and the readings stabilized, the realization spread across control rooms in quiet, synchronized disbelief. Atlas wasn't there. No residual debris, no diffused dust trail, not even the thermal echo of disintegration. The sky was simply blank, as though the object had never existed at all. ESA's solar orbiter caught one faint anomaly a few hours later, a ghostly spike of magnetic turbulence sweeping outward from the far side of the sun. It lasted less than 2 minutes, resembling a wavefront rather than an explosion. No accompanying heat, no light, just motion, as if something had moved through the solar field and left a fingerprint behind. NASA's Deep Space Network searched the predicted outbound corridor for reflections. Nothing. Hubble turned its sensors toward the coordinates at 0.38 astronomical units, then again at 0.41. The same. Silence. By mid-morning, the official word settled into the data channels. No reacquisition. The naturalist camp called it dissolution, a comet destroyed by solar radiation, vaporized entirely at perihelion. A tidy ending, mathematically plausible, emotionally convenient. But the energy calculations don't agree. For an object of Atlas's density, the heat at that distance, even at 0.36 astronomical units, would sublimate volatiles, not erase a metallic core. The absence of debris defies thermodynamics. Nothing so dense could disappear so completely without trace. The plasma signature recorded by Parker Solar Probe should have caught the residue. Yet it didn't. The silence isn't evidence of destruction. It's evidence of departure. Now, across agencies and institutions, the arguments have stopped. What remains is a kind of hush, not consensus, but surrender. In the absence of data, certainty evaporates, but somewhere in that vacuum a quiet awareness has taken root. That we may have witnessed the bending of a rule, not its breaking. Because the universe has always been lawful. Predictable, measurable, explainable. Atlas simply reminded us that laws are only as strong as the phenomena that obey them. Perhaps this is how every discovery feels at first, not like revelation, but like loss. The loss of a framework, a boundary, a comforting illusion that the cosmos plays by rules we can write down. Atlas didn't destroy those rules, it expanded them, quietly, elegantly, without even needing to speak. If it was a probe, it never signaled. If it was natural, it redefined nature. If it was something else entirely or something between the two, then it sits now beyond the sun, invisible, carrying knowledge we don't yet have words for. There are still hard drives full of readings, still terabytes of ultraviolet noise, still arguments waiting to be formalized into papers. But deep down, every scientist involved in the chase knows that the real story isn't in the data. It's in what we didn't see, the blankness, the absence, the impossible precision of an object that arrived, performed, and left without error. In some corners of the scientific community, they're already renaming it. Not a comet, not an asteroid, just the visitor, a neutral word for something that defies classification. The public will forget. The media will move on. A few documentaries will air. A few debates will fade into academic silence. But somewhere in the back of every observatory, a new question will haunt the next generation. How much of the universe is observing us back? Because the truth is simple and cruel. Every time we look outward, we're also seen. Our telescopes don't just measure, they announce. And if 3i Atlas truly came to measure us, then its departure isn't an ending, it's an evaluation. In the early hours of November 4th, long after most arrays had powered down, a small amateur telescope in Namibia picked up a faint streak just above the solar limb, a dim line moving outward, green in filtered light, leaving no debris, no tail, no sound. It lasted seconds, then it was gone. The observation remains unverified. Maybe it was noise, maybe a flare, maybe for a moment the universe allowed one final glimpse. But if that streak was real, if 3i Atlas truly survived its solar passage, then it's still out there, beyond the light, beyond certainty, writing its own laws. And perhaps that's the most honest way the universe teaches. Not by revealing the truth, but by showing us that the truth moves,